Hello. In this video, we are going to introduce the concept of series as we continue towards that goal of finding ways to approximate functions to make them easier to work with. So, as a review from yesterday, a sequence is an infinite ordered list of terms. Most often numbers, but just a list of things that goes on infinitely. So we often write it as an A sub n, and that equals the list A1, A2, A3, A4, and so on. Eventually we'd have the nth term, and we keep going as the list never ends. And then what a series is, definition of a series, is that a series is the sum of an infinite list of terms. So it's taking a sequence and summing them all up. So there's these two things that are going to be talked about, and we're going to actually add on a third, which is another type of sequence we use to talk about the series. But first, just telling the difference between the sequence and a series. To write out a series, we use summation notation, and we have a lower bound, typically 0 or 1, can be anything. And the upper bound is going to be infinity, because it's an infinite sum. And then we would put our sequence that we're adding up after the summation notation. And this means we're taking that list of terms, A1 plus A2 plus A3 plus A4 plus continuing to add plus AN plus and so on. So we're adding up an infinite amount of things. It's a little bit of difference between what is happening with the sequence and what is happening with the series. And we're going to keep coming back to this idea of using the sequence to talk about the series. One comparison for things we've already talked about is all through the end of Calc 1 and all we've done with Calc 2 so far. We had a function that we could talk about. The function is increasing, the function's decreasing. We could talk about the slope of the function. We could talk about the limits of functions. The function has all these properties going on. And then using these properties of the function, we introduced the idea of the integral of a function. The comparison between a function and an integral is very similar to the comparison between a sequence and a series. We really can't talk about the series without talking about the sequence, but they are different things. And we'll see some examples trying to piece together how they relate and how they are their distinct items. But relating back to something we've worked with, sequences and series, their difference is very similar to the difference between a function and its integral. So the next thing we introduced to be able to talk about this infinite series is we're going to define what is known as partial sums. Sounds like partial fraction decomposition. Partial just meaning breaking it up a little bit. So the kth partial sum is the sum of the first k terms of the sequence. We are going to denote the partial sum as S sub n, or S sub k. And so this means the sum from our starting value up to k of our sequence. And this means a sub 1 plus a sub 2 plus a sub 3 plus so on until we get to that kth value. And then we stop. It does not continue on any farther. So the first partial sum would be the sum from n equals 1 to 1 of an. Well, if I'm adding only the first term, that is just the first term of the sequence. The second partial sum, n equals 1 to infinity, n equals 1 to 2, a sub n, is those first two terms added together. S sub 3 is the sum from n equals 1 to 3, a sub n. So the first term, the second term, and the third term added together. And what you might be seeing is that we're creating a sequence here, where the first partial sum is the first term. The second partial sum is the sum of the first two terms. The third partial sum is the sum of the first three terms. So we create this sequence of partial sums, which is the sequence formed by those partial sums, S sub k. So now what we have is we have three things going on. We have a sequence, which is just going to be our list of terms that we're looking at. We have a series, which takes the whole sequence and adds it together. And then the partial sums take the sequence and add them together bit by bit to create a new sequence. We're focusing on this infinite series, but we're going to use the sequence and the sequence of partial sums to help us talk about these series. Because we're trying to add an infinite number of things together. And ultimately, does it make sense to talk about the sum of an infinite set of terms? Does it make sense to take an infinite number of things and add them all together? Well, we need some structure to be able to do that. So our first example is this sum: 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, and so on. So the sequence here that is happening is just those whole numbers. The sequence a sub n is n, which is the sequence 1, 2, 3, 4, 5, and so on. So this is the sequence. The series, n equals 1 to infinity, a sub n, is just what is written up here. It's the taking those 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus so on. So this is the series. Last time we were able to talk a lot about the sequence converging or diverging. And we know this sequence, limit as n goes to infinity of a sub n, is infinity. So the sequence n diverges. What we talked about most of the last section. But can we talk about convergence or divergence of a series? Meaning, can we talk about a series where we're adding up an infinite number of things, where that series comes out to a number, a single finite number, or it doesn't? Divergence. And that's where the sequence of partial sums comes in. The sequence of partial sums, we say, okay, S sub 1 would then be the sum of the first term, 1. S sub 2 would be 1 plus 2, which is 3. S sub 3 equals 1 plus 2 plus 3, which is 6. S sub 4 is 1 plus 2 plus 3 plus 4, which is 10. And so our sequence, S sub k, is the sequence 1, 3, 6, 10, 15, 21, and so on. So this is the sequence of partial sums. And if we look at this sequence as I keep building up k's, this sequence, if I looked at the limit of this new sequence, n goes to infinity of S sub k, pretty safe to say this goes to infinity as we keep adding more and more on with every next term. So the sequence of partial sums diverges. And we've got these two things diverging. We have the sequence and the sequence of partial sums. This should be as k goes to infinity. That both diverge. And since these two things are so highly related to the series, probably a good guess, the series diverges. And we will see different ways later how we can say that to be true. But if we're always adding an infinite number of things together, will we ever come to a finite number? Well, think about integrals. They're a little bit different, but the integral ultimately was trying to add an infinite number of tiny rectangles together. And we would get those infinitely many tiny rectangles to come out to a finite area under a curve. So it is possible to add an infinite number of things together and get a finite number. So when does convergence happen? So we're going to look at another example. This example is 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. The sequence here is the sequence 1/2 to the n. Because I'm between each term, I am multiplying by 1/2. So we have a geometric sequence that is 1/2, 1/4, 1/8, 1/16, and so on. And we know that the limit as n goes to infinity of 1/2 to the n is 0 by it being a geometric sequence. So the sequence of 1/2 to the n converges. Looking at the series, that is what we have written up here that we're looking at. That is the sum of these 1/2 to the n. This is equal to 1/2 plus 1/4 plus 1/16 plus 1/8 plus 1/16, and so on. And we can see here that we're adding on things, but we're adding on things that are smaller and smaller. Last time, what we added on kept getting bigger. But this time they're getting smaller and smaller, so maybe there's a little bit more hope of convergence. Looking at the sequence of partial sums, S sub k, S sub 1 is the sum of the first term, that's just 1/2. S sub 2 is 1/2 plus 1/4, which is 3/4. S sub 3 is 1/2 plus 1/4 plus 1/8, which is 7/8. S sub 4 is 1/2 plus 1/4 plus 1/8 plus 1/16, which is 15/16. And continuing on, if we look at this pattern, the denominators are powers of 2, and the numerators are 1 less than the denominator. So the sequence of partial sums is the sequence of those powers of 2 and the power of 2 minus 1. So there is our sequence of partial sums. If we look at the limit as k goes to infinity of 2 to the k minus 1 over 2 to the k, if we use some growth rates here, the growth rate that's the largest in the numerator and denominator is the same thing. So this limit actually works out to be 1. So the sequence of partial sums converges. And so we have both the sequence converging and the sequence of partial sums converging, which kind of points to maybe the series n equals 1 to infinity of 1/2 to the n converges as well. And this actually is definition. The definition is given a series that is adding up an infinite number of terms, the series converges if the sequence of partial sums converges. So if the limit of S sub k, or S sub n in this case, they switch their k's and n's, converges. And it diverges otherwise. So in this first example here, the series 1/2 to the n converges because S sub k converges. So the series 1/2 to the k equals 1 to infinity, converges because the sequence S sub n, switching them out, switching the n's and k's, which is 2 to the n minus 1 over 2 to the n, converges because the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n equals 1. So the series converges because the sequence of partial sums converges. And for the previous example, the series, switching out the k's and n's again, k equals 1 to infinity of k, diverges because the partial sum, which was the sum of the first n terms, not really a good pattern to be writing here, diverges because that limit does not exist. Limit k goes to infinity of s sub k, or n goes to infinity of s sub n, equals infinity. So there's the sequence, and the sequence can converge or diverge on its own. But when we want to tell about the series convergence, we're looking at the sequence of partial sums. And there's 3 different things. We'll see some examples in the next video of looking at the sequence of partial sums to help us determine if a series converges.